Hello, and thank you for joining us today as we review cardiac imaging on a mouse using the Prospect T1 system. This presentation is being brought to you by Syntica Instrumentation. During the presentation today, we hope to show you how the Prospect T1 system can be used for both systolic and diastolic functional measurements in a mouse, looking at both the left and right ventricles, focusing then on the aorta as well as the pulmonary artery, and finally taking a look at flow through both the mitral and the tricuspid valves. First, the mouse is positioned into the knockdown chamber if using a gas anesthetic such as isoflurane to do the imaging session. Once anesthetized, the animal should be moved onto the animal platform. This stage is heated to help maintain the temperature of the animal. As well, there are ECG electrodes to help provide both respiratory and ECG signals. Each paw should be secured to the animal platform using a small amount of ECG gel, as well as some tape to secure the paws. Once all of the paws have been secured to the animal stage, the rectal probe should be inserted to monitor the animal's body temperature throughout the imaging session. A small amount of lubricant, such as the ECG gel, may be used to help the insertion of the probe. The probe should be inserted carefully and then secured in place using some tape. A depilatory cream, such as Nair, should be used to remove all of the hair over the area to be imaged. Here we've removed the hair from the chest, using wet gauze to remove both the cream and any hair, leaving the chest skin fully exposed. Once we're ready to image, ultrasound gel should be placed over the area of interest. Here, again, we're going to do some cardiac imaging. With the gel in place, we can move the probe into position. So here we want to consider how the single element transducer will be wobbling, pulling the area with the barcode towards us, with the S-sharp logo pointed away from us. To do a long axis view, I'm going to tilt the table with the animal's right-hand side tilted down and the probe positioned right over top of where the heart would be viewed. In B mode, once we push play, we can see that ECG and respiratory signal coming across. We're going to now move the animal probe stage up into position and begin to move the probe such that we can see the heart view. Using the micropositioners, we can make small movements to align the probe in line with the left ventricle. Here we can see the ventricle nice and open, as well as the aorta in view. I can see that a small rotation of the probe may be needed to get a true long axis view. I rotate slightly counterclockwise, again using the micropositioners to pull that left ventricle back into view. This did not help, so I'm now going to move through and rotate clockwise about the same amount, again using those micropositioners to ensure that my left ventricle is in a true long axis view. If needed, I can grab the probe holder itself and move it in line, and here we can start to see a very nice long axis view. Again, focusing on the ventricle and the apex being as open as possible, and the aorta and the aortic root clearly in view. I'd now like to move to show you what was captured on the screen during that acquisition. So here again, you can see that the apex is very open along with a nice open ventricle. And as well, the aortic root as well as the aortic valve can be seen flapping while we're imaging. Once we're finished with the long axis view, it's actually quite simple to do the pulmonary artery. By simply pulling the animal and the whole animal stage towards us, we're able to see the pulmonary artery very clearly coming out of the right ventricle. We can simply save the image and move on. Moving into color Doppler mode, we're able to visualize the flow through the blood vessel using an acronym called BART, blue away and red towards. Here I'm just changing the size of the sample volume moving it over top of the pulmonary artery and looking for the strongest blue signal that we can see. If aliasing occurs, then I would change the PRF or pulse repetition value to increase our velocity scale. Again, showing a nice blue signal coming through the pulmonary artery. And again, we can save that image very quickly. Moving now into pulse wave Doppler mode. This will allow us to visualize and measure the velocity of the blood flowing through that pulmonary valve. Placing the sample volume right at the valve leaflets or the valve opening, we're able to get a very strong signal on the pulmonary artery. Moving the baseline up such that we can see the blood and the velocity scale flowing away from the transducer, so flowing in the negative direction. I can spread my time scale out by simply left-clicking and dragging to the right. And what we're seeing here is a really strong signal, and that peak that we're seeing at the top is actually the valve leaflets closing, pulling some of the blood backwards. This is not regurgitation. If we had regurgitation, we'd see almost as high of a velocity in the opposite direction. Again, moving into what was captured on the screen, here again we can see the pulmonary artery and the valve leaflets. In color Doppler mode, again I'm changing the size of the sample volume and moving over top of the pulmonary artery. Again, following the acronym BART, blue away, red towards, we're seeing the blue flow of going through the pulmonary artery. At this point, we're seeing some aliasing, so we're increasing the PRF for the pulse repetition frequency. That increases our velocity scale, and again, we'll see the nice strong blue coming through the pulmonary artery. Now moving into pulse wave Doppler mode, we can see our color Doppler scout image on the upper right-hand side, placing our sample volume right in the middle of the pulmonary artery, adjusting our angle correction such that it's in line with blood flow. We can then move into pulse wave Doppler mode, where we're both able to see and hear the Doppler signal coming through the pulmonary artery. Changing our velocity scale, moving our baseline, we can start to see the nice clean laminar flow. Changing our time scale, we're able to visualize this envelope very clearly. Once we're finished looking at the pulmonary artery, we then want to move back to the long axis view by pushing the animal away from us. Here we're trying to get to the short axis view, and what we'll do is release the rotation clamp on the probe, rotate the probe 90 degrees in the clockwise orientation, and resecure that button. Now we should have a nice short axis view looking for a complete circle rather than an oblong D or an oval. Here I'm going to use the micropositioners to move up and down the ventricle looking for the papillary muscles. This will give us an anatomical location to ensure that we're able to take the same image every time on each mouse. Here again on the screen capture software, we can see the nice round ventricle with the papillary muscles in view. Moving now from B mode to M mode, we want to look at the motion of the heart along that single sample volume line, positioning the sample volume right in the middle of the ventricle such that the papillary muscles are coming in and out of view through systole and diastole. Moving into M mode, we can see that motion along the single line in view. Stretching out our time scale, we can begin to see and trace those wall movements again over time. Seeing the papillary muscle come in and out on respiration on the posterior wall is exactly what we'd like to see. A closer view, again from the screen capture software, we can see that sample volume placed right in the middle of the ventricle, and we can see the motion of the heart along that line over time. Spreading our time scale out, we're able to then trace both the posterior and the anterior wall through the spectrogram. Moving now from the short axis view, we want to move into the apical four-chamber view. We do this by dropping the animal away from the probe, tilting the animal's right shoulder all the way down, and rotating the probe such that the probe will be coming in right at the apex of the heart, and tilting the probe as well. Okay, again, we want the wobble to go from animal's right to left across both the left and the right ventricles, tilting the probe and moving the animal right up into position. Again, with the probe in position, we'll move the animal up such that the probe touches the gel on the surface of the animal's skin. As we move the animal into position, we can see the image updating real time on the screen. And here what we're looking for is the contraction of the left ventricle with the septal wall clearly visible. Moving now into Doppler mode, we can use color Doppler to visualize the flow both through the mitral and the tricuspid valves. Moving now into pulse wave Doppler, we're able to place the sample volume right over the inflow for the mitral valve, seeing the biphasic peaks of the mitral valve inflow. Here on the screen recording software, we can see a better view of both the E and the A peaks as well as the aortic outflow. The Prospect T1 system is also capable of doing tissue Doppler imaging. Here you can see the sample volume placed right at the mitral annulus, and the resulting tissue Doppler signal is shown, which is exactly the inverse of the pulse wave Doppler, showing both E' and A'. We are also able to visualize the tricuspid valve flow in most animals. Here seeing the very strong red color Doppler signal going from the right atrium into the right ventricle. Here we can see the very characteristic tricuspid valve flow having a lower E than A peak. Moving now to the aortic arch, we've tilted the animal's left side completely down, moving the probe over to the animal's right-hand side with the single element wobbling basically from head to tail. As you can see, we can see the ascending aorta as it curves around and identifying the 3 different branches. Using color Doppler, I'm again able to visualize the flow as it moves from the ascending aorta into the arch. Here for a closer look at the color Doppler signal. Now moving into pulse wave Doppler mode, we can place the sample volume right along the aortic arch and measure the flow velocity through this area. This may become important if we had a model such as TAC, transverse aortic constriction, in which we wanted to measure the velocity of the blood flow through the stenosis. Here we'd place a sample volume right at the stenosis opening, which we would be able to visualize with ultrasound, and we would see the flow through that vessel or through that opening. Here we're seeing flow through a normal transverse aorta, and we're seeing nice, clean laminar flow. If it was a TAC model, we'd see this fuzziness within the aortic signal and an increase in the velocity as well. Here we can see the flow through the aortic arch as well. Changing the time scale, we can see there's nice laminar flow. This brings us to the end of our presentation today, showing cardiac imaging using the Prospect T1 on a mouse. I hope you enjoyed today's presentation, where we looked at both systolic and diastolic functional measurements, looking at the left and right ventricles, studying flow through the aorta, pulmonary artery, as well as the mitral and tricuspid valves. Today's presentation was brought to you by Syntica Instrumentation. Syntica's goal is to link scientists with precision tools for research through expertise in science, engineering, and support. I'd like to thank you for taking the time and joining us today. Should you need any more information, please feel free to reach out to us at info@syntica.com or at the phone number listed on the slide in front of you.